organized by the Department of Mathematics, School of Advanced Sciences, SAS, VITAP University, which runs in online mode for 2 weeks starting today. With this brief welcome, I would like to request Dr. Santanu Mandal, Dean, School of Advanced Sciences, to introduce about the school and the program.
Thank you, Dr. Martha. Good afternoon, everyone, and good morning, Dr. Matthew. I'm Shantanu Mandal, Dean of the School of Advanced Sciences and Head of the Department of Mathematics, VITAP University, India. On behalf of the School of Advanced Sciences, I would like to extend a very warm welcome to the dignitaries present here, my colleagues, dear students and participants. School of Advanced Sciences has 3 departments: mathematics, physics, and chemistry. Our main strength is our faculty member. Near about 50 faculty members we have. All faculty members having the minimum qualification PhD, and some of the faculty members postdoctorate within India and outside. Now, in our school, actually, near about 40 research projects, already few of them completed and few of them are running. And in the section of the publications, near about 110 publications we have, SCI and Scopus. It is with the VITAP affiliation only. We have full-time research scholars near about 60 in our school. It is a PhD research scholars. And our school is offering 4 programs. Dual degree program is a BSc MSc data science with exit option VSc after 3 years. And this program with collaboration with Latent View Analytics, one data analytics, data science related company. We have a PG program, MSc Data Science, in collaboration with the Latent View Analytics. We have MSc Chemistry PG program in collaboration with Mitsui Kinzaku, one Japanese company. Recently, we signed on MOU with this company. And we have PG program for MSc Physics. Instead of these programs, UG and PG, we have PhD programs in math, stat, physics, chemistry. And lot of collaborations as of now we have, because you know the VIT brand, Valor Institute of Technology. So here, this foreign university collaboration, etc., it is relevant for all campuses of the VIT. So regarding campus placement scenario, is all 4 campuses students can take the experience of this all company that we are bringing here. So it is a common placement actually for overall 4 campuses. Okay, whoever the students, which campus doesn't matter. So if you are eligible, you can sit in the campus for this VIT group. So more and more facilities we have, laboratories we have, and I may request you may visit our website, school website. You may get the deep insight of our school. So today there is a session, is a guest lecture, and then invited talk maybe, and then research talk kind of, that we are organizing out of one series of webinar. Okay, so it will last next week. Tomorrow also another session we have. Okay, so in this occasion, we are delighted to have with us Dr. Matthew, University of Manchester, UK. We welcome you, sir. Dr. Matthew is going to deliver one talk on variational problems in machine learning. Dr. Matthew is a lecturer in applied mathematics at University of Manchester and is currently visiting the Isaac Newton Institute in Cambridge as a part of the program on the mathematics of deep learning. He works on optimal transport and large data limits of graph-based variational problems that arise in semi-supervised and then unsupervised learning. Dr. Matthew completed his PhD at the University of Warwick. Previously, he was a research fellow at the University of Cambridge, and he did postdoctoral research in Carnegie Mellon University. So with this brief introduction, I request Dr. Matthew to conduct this session. Over to you, sir. Thank you.
Okay, thank you very much. I mean, thank you for the invite and thank you for the kind introduction. So let me just share my slides. All right. Okay, so let's get the chat up so I can see. Okay, so please feel free to interrupt me if you have questions. I've got the chat so I can see if you write in the chat or just sort of unmute yourselves and interrupt me. I'm very happy to take your questions. Okay, so I'm going to give an overview on some machine learning problems that can be posed as variational problems. I'll give some asymptotic results because this is kind of what I'm interested in. But the aim of the talk isn't really to give a sort of a technical talk, it's more to give kind of an overview and to maybe to give a hint at what some of the techniques that one can use to prove these results are, but not really to go into sort of the details. Okay, so I sort of quite ambitiously put together about 6 different methods. I think we won't have time for all of these, so I'm imagining we'll end up cutting at least a few of these. But I'll start off anyway talking about the k-means method, which is quite a classical method, which I think at least some of you will probably know quite well. And then I'll move on to the graph-based methods, and give a few examples of what the sort of mathematical analysis can say about these sort of problems. Okay, but maybe I should start by saying, well, why do we even care about sort of large data limits? Okay, so let's take a very abstract problem. Say we know we have some sort of data set dn and we want to make some sort of inference about this data set. So this could be, we want to find some labels, we want to find clusters, whatever the problem is. Okay, so we'll have some estimate un, which we find using some method. Okay, and this estimate un is based on our data set dn. Okay, so why do we care what happens when un? Why do we care what happens to un as n goes off to infinity? Well, I mean, I would sort of motivate this in sort of several ways. I mean, the first thing is this can be posed as a consistency question. So we can imagine, well, maybe there's a true solution. Let's call it u dagger. And can we show that un is converting to u dagger? In machine learning type problems, this is actually quite a strong statement. I mean, what does it really mean that there is a true solution? If we're trying to estimate some labels, I mean, is there a true label? And possibly not, in which case we can kind of weaken our statement and say, well, can we instead look for convergence? So instead, can we say, okay, un is going to converge to u star, and what can we say about u star? Is this going to solve some sort of limiting problem where we don't have data, but maybe we have problems distributions instead? Okay, but both of these sort of consistency and convergence, they really give us an idea of how robust the method is. So this is just a question of, if you already have a lot of data, if someone gives you one more data point, is your estimate going to change a lot? Of course, you would hope that this isn't going to change a lot, because you would hope that you're kind of stabilizing, your method's sort of stable. Okay, and then lastly, there's a sort of numerical sort of viewpoint, and understanding these sort of large data limits can potentially open up numerical methods. So, for example, things like preconditioned Crank-Nicholson, these are designed for the continuum models, and they're in particular defined for infinite dimensional spaces, which means that they're kind of overcome the cursive dimensionality. This isn't something that I really used to go into, but it's kind of a motivation for some of the work that I do. Okay, so let's kind of start at the beginning. So what is a variational problem? So a variational problem is just kind of a fancy way of saying we want to minimize or maximize some given objective functional. Okay, so the objective functionals we have, so I'll always note them en, and they're going to depend on our data set dn. Okay, and then we're just looking at problems which we can write as un is equal to the minimizer of this energy, which depends on our data set dn. Okay, so in some sense, un is the best estimate when we're measuring by en. Of course, what I'm not really going to say as well is en a good choice. And this, I mean, this can perhaps be tied back to the sort of asymptotics and say, well, I mean, if it has kind of nice properties, then it's a good choice. I mean, this can be motivated. The choice of EN can be motivated from a model, or it can just be motivated by sort of, behavior which we would expect. Okay, and then I want to briefly talk about one of the techniques we can use to analyze variational problems. So again, let's stay very abstract, and let's say we have a sequence of energies which we're trying to minimize. Okay, so the blue curve and the green curve are two instances of this energy which we're trying to minimize. And you can see the blue curve is more oscillatory than the green curve. So the green is sort of varying quite slowly. The blue one is much quicker. We can imagine maybe as n increases, the energy which we're trying to minimize is oscillating faster and faster. And what we want to know is, okay, is this convergent to anything? So when something, we have a sequence of functions, well, the first thing we can ask is there kind of a limit in a strong sense? So the answer to this is no, there is not. You can see because we're oscillating, right, then we can't find two sort of bounds and sort of squeeze the limit between these two bounds. We can look at weaker notions of convergence, however. So the weak notion of convergence is to sort of average out over the oscillations. So the weak limit will be given by this red curve here. You can see this is just, we've just averaged out over the oscillations. So if we look at around here, well, we spend as much time above this curve as below this curve. Okay, so this one's the weak limit. But let's remember what we care about. So we care about the minimizers and the minimum. Okay, so let's look at where the minimizers and the minimum are. So for our energies, right, the minimizer and the minimum are always at this point here. But our weak limits, right, the minimizer and the minimum is over here, right? It's where the red curve is. Okay, so you can see, right, this isn't the right notion of convergence because we're looking in the wrong place. Okay, so the gamma convergence is kind of the right notion of convergence, right? And the gamma limit is this black curve here. So somehow this is, the limiting lowest in the continuous envelope. So it's the function which kind of bounds from below these the sequence of oscillating energies. Now you can see that the black curve has the minimizer and the minimum in exactly the right place. So of course, gamma convergence has a proper definition, which I won't really sort of talk about, but this is what it is. But the picture, it kind of explains it better, right? So it's just the black curve. Okay, and again, there's a theorem which kind of again just supports this this picture, and this just says that if we have UN, which are a sequence of minimizers of our energy, then as long as we have gamma convergence, then we have that the minimizers converge. Okay, and so the minimum converges, and furthermore, that the minimizers will also converge up subsequences. Okay, so this is kind of one of the few technical slides. I'm now going to talk about some sort of machine learning problems. So I'll start with the k-means method. Okay, so this is probably a recap for some people. Maybe other people haven't seen this before, so I'll try and go sort of fairly slowly still. So the k-means method, right, we have a data set. So we have all these, let's call them feature vectors, xi. So we have n of these. There's d-dimensional vectors. And what we want to do is we want to divide these feature vectors into k subsets. Okay, so we're going to do this by minimizing an energy. The energy we'll minimize is this En. Okay, so this En is a function of z. So each of these z's, so we'll have k of these z's, so z1 up to zk, and each of these zi's is itself a d-dimensional vector. Okay, and then the energy we define is we take our feature vector xi, we look at the z which is closest to it, then we compute the distance, we square the distance, and then we sum over all these feature vectors. Okay, and then what we sort of say is that the choice of z which minimizes this is somehow our best choice. Okay, and we will call these zj's cluster centers for a reason that's going to be obvious in the next slide. Okay, so then how do we actually do our partitioning? Well, we just do our partitioning by assigning each feature vector to the cluster center that's closest to it. Okay, and this is the k-means label. Okay, so I have a little sort of video. I guess let me go back to the start. Okay, so we start off with our data set. So each of these black points, right, these are feature vectors. These are our xi's. So the k-means algorithm works by, initially, you would assign a random label. So, okay, so here I've colored each of these feature vectors, either red, blue, or green, just randomly choosing one. And then I've computed the cluster center for the red set, for the blue set, and for the green set. So, okay, so the circles in the middle, these are the three cluster centers, and of course they're all pretty much in the same place, just because my data is kind of, you know, the initial labeling is kind of spread out more or less uniformly. Okay, in the next step of the k-means algorithm, I will repartition the data. So I will, for each feature vector, so let's take this feature vector up here, I will look at which cluster center is closest to it. So of course, for this feature vector here, I can see that the closest feature, so the closest cluster center is this blue circle here. So this is going to turn blue. And again, I can see like everything down here is going to turn green. So if I just go one step forwards, okay, then I have greens at the top, greens at the bottom, blues at the top, and then there's a kind of thin strip which gets turned red. Okay, and then I recompute my cluster centers by just taking the average over all the green ones, the average over all the blue ones, and the average over the red ones. Okay, then I repeat this method. So now I will look at another feature vector. So let's maybe take these two feature vectors here, right? And I will look at which cluster center is closest to it. Okay, the closest cluster center is going to be the red one. So these 2 points here are going to turn red, okay, and so on. So if I go one step further, right, you can see they turn red. I've recomputed my cluster center, okay, and now my cluster centers have moved. And if I keep going, right, you can see eventually I sort of stabilize, and I just identify this is one cluster, this is one cluster, this is one cluster here, and each of these cluster centers are in the middle. So this is the k-means algorithm. I think it provides a way of labeling data. Okay, so I'll sort of quickly talk about the convergence results. So now we will assume that these xi's are distributed from some measure. So actually here, the three, this measure here is just going to be 3 Gaussians. I mean, it's just a tiny example. But in general, it could be more or less anything. Okay, and what we can show fairly easily is that so if Zn is my cluster centers for the data for the data set with n data points, then this is going to converge up to subsequences to the cluster centers, which solves a sort of continuum problem, where instead of having data, now I just have the probability distribution. So the only difference between this E infinity and this En was that this summation on the previous side now becomes an integral with respect to a probability measure. Okay, so one can now sort of maybe start to sort of generalize this sort of method. So this is sort of motivated by the question, what if we want to have cluster centers and data that are in different spaces? Okay, so in particular, we're thinking of a problem where we have k unknown curves, and we don't know a priori whether our observations are going to be which curve our observations are sort of attached to. So let me just show the picture. Okay, so here, imagine this is sort of time on this x-axis, and this is space on this axis here. Okay, and so at each time point, we get an observation from something. Okay, so that gives us, so our data is going to be a point in time and a point in space. But we have multiple objects that are moving around, and we don't know which object we're detecting from. So in this case here, I imagine we have 3 different objects. So we have like this blue object, here we have this red object and this green object. And okay, so we have an observation from each of these objects. We don't know which one it's coming from. And so what we want to do is simultaneously solve the problem of identifying the observations with a particular object and finding out where this object is. Because of course we don't observe the blue lines, the green lines, or the red lines. Okay, so again, what is going to be our variational problem? So now we kind of have the same, well, I guess a very similar to the first term, where so Zj are sort of our cluster centers, but now these are functions. So these are functions from 0, 1 into you know, I guess in general into RD, but in the previous slide, right, it was just R1. Right, so what we would do is we would evaluate our function, okay, at the observed time and look at the difference between where we observed it. Okay, and then we're associating the observation with the object which is closest to it. Okay, this in itself won't give us a very isn't a very good problem because it will essentially just overfit. So what this means is that what we'll end up doing is we'll end up just interpolating between all these data points. Okay, and so we kind of learn nothing. So what we want to do is we want to kind of smooth our trajectories out. So we do this using well, it's a H1 semi-norm, so just a penalty on the derivative. So this kind of forces us to have like a much smoother interpolation between the data. Okay, so the algorithm itself is more or less the same. So I've got a video on the next slide, so I'll just show this. But we start off by initially labeling all our data. Okay, and then we solve what is essentially a spline smoothing problem. So if we know the association of the data, right, then what we want to do is we want to solve this, well, we're taking out the data association problem. So now we're just trying to smoothly interpolate between our observed, between our observations, okay, Ti and Xi, okay, and we can do this kind of using sort of standard methods. Okay, and then we sort of repartition the method, repartition the data, and then we go back and we refine our cluster centers and we just repeat this into convergence. Okay, so our black points are our data, the green, the dash curves are kind of the true solutions, which we don't know. And then, okay, and so then if we apply the k-means method, right, so we initially label all our feature vectors just randomly, and then we compute the kind of the smooth approximation. So again, so the solid curves are the smooth approximation. You can see everything's kind of like in the middle. This is because, of course, all our data is kind of uniformly labeled. But you know, if we go back and we relabel our data based on the closest curve, you can see quite quickly, well, okay, we start to assign mostly blue over here, mostly green over here. Okay, the red's still a little bit chaotic. If we sort of go one step further, right, we can kind of see that we slowly start to recover everything and everything. I mean, of course, we don't end up exactly recovering our true solutions. I mean, it's a little bit smoother. So here you can see with the green, the trajectory actually is a little bit more varied than what we recover. We kind of don't quite get the whole curve, but okay, it's approximately what we're looking for. So I'll go quite quickly over this. So this is the more abstract way of setting up the problem. So now instead of using a very explicit, well, say like distance between the observations and the cluster centers, we can make this more abstract and just say, you know, it's just some function which measures the distance. Okay, and this has to satisfy some assumptions, which I won't go into. We have some sort of regularization on the cluster centers, and this then will be our abstract problem. Okay, and what we can show is that, you know, again, up to subsequences and with probability 1, that the minimizing the finite data problem is going to converge to minimizing the problem where these solations have been replaced by an integral with respect to the probability measure. Okay, so let me go on to graphs. So this is probably my main area of research at the moment. Okay, so I'm particularly interested in semi-supervised learning problems. So this is the problem of finding missing labels. Okay, so now we will start with a data set which will consist of feature vectors as we had before, and we would assume we have a subset of labels. Okay, so we don't have labels for every feature vector, but we have labels for some of them. Okay, so the ones which we do have labels for, we index by this Zn. So this is just a subset of 1, 2, up to n. So typically, maybe, you know, we have labels for the first 10 feature vectors say, okay, but then everything from 11 onwards, we don't know. Okay, so our objective then is to learn what these missing labels are. Okay, and the idea is that the data kind of has a geometry, and this will help us find the missing labels. So we don't know what the geometry is because we only have observations, but maybe we can kind of learn the geometry from the unlabeled feature vectors. Okay, so an example of this would be if the data lies in a low dimension manifold. So these feature vectors could be in RD. If we're imagining that these feature vectors are actually images, well, actually the dimensionality is probably much lower. And so, okay, so somehow, if we can use this sort of information, then we can potentially find a better solution. And so the next slide has like a motivational example, which, you know, hopefully you'll kind of see what we can gain by using unlabeled data points. Okay, so let's imagine like a very toy problem. Let's say we have two feature vectors which are labeled. We have a red one and a blue one. Now, if I want to divide my state space up, right, the obvious thing to do is just to put a line in the middle of it. In case anything on this side I would class as red, anything on this side I would classify as blue. Okay, now let's say I have some unlabeled data, and my unlabeled data looks like this. Okay, so if I apply my classification rule, right, this is what I get. But you can kind of see this isn't really a very good rule. You can see actually it'd be much better if I moved my line here, if I moved it over into this gap here, right, and now this seems much more reasonable. And what I've done here is I've taken into account the geometry, and I've used that to improve my labeling estimate. Right, okay, so how do we do this kind of properly? So we use graphs. So for a graph, we need both nodes and we need edges. So the nodes are just going to be the feature vectors. So let's say I have six, a very small data set of 6 data points. Right, so okay, so these then are my, form the nodes on my graph. And then what I'll do is I'll place edges between all of these nodes and I will weight them. So I'll weight them according to some function eta, and I think for the purpose of this talk, you can just think of eta as being an indicator function based on the distance between the two edges. Okay, so in particular, if these two edges, so if x5 and x6, if these are close, if these two nodes are closer than some epsilon, which I would have to specify, then I would have a positive weight for my edge. Otherwise, I would have 0. Right, so then, okay, I throw away all edges with 0 weight, and what I should end up with is a graph that's a bit more local. Right, so this epsilon is something which we have to choose, and this we'll sort of come back to later. But just for now, I'll just say that, of course, we're going to need a lower bound on epsilon, because if epsilon is very, very small, then, of course, I'm not going to have any edges in my graph. So I'll always kind of assume that the epsilon is big enough that the graph is connected. Okay, so if I think probably the smallest edge is probably between maybe x4 and x5. So, of course, if epsilon is half the distance between x4 and x5, right, then none of these edges are going to be, there's going to be no edges in my graph. Okay, so we assume that epsilon is kind of sufficiently big that everything is, the whole graph is connected, which just means I can get from one side of the graph to any other side of the graph. Okay, so what is the problem then? So, okay, so we have a data set, we have a subset of labels. So here I'm just going to assume the first capital N are labeled. And what I want to do is find, what somehow is the best function UN that agrees with the labels. Okay, and then sort of interpolates between these known labels. Okay, so this is this sort of P-Laplacian regularization problem. This was proposed by Zhu, Garamani, and Lafferty. So they proposed it actually for P equals 2, and then Zhu and Shopkoff proposed it for like a general P. So what they said is, okay, let's minimize this ENP, okay, subject to taking these constraints. So why is this perhaps like a natural energy to use? Well, okay, so let me just see. So, okay, so what we want is that if two feature vectors are similar, then they should have similar labels. So what we've done is we've captured the similarity between the feature vectors in these graph weights here. So if xi and xj are very similar, this means wij should be very big. Okay, so if we're trying to minimize this energy here, well, when wij is very big, this should mean that u and xi minus u and xj is very small. Okay, so naturally this is kind of like, I guess, a reasonable choice of energy which we want to minimize. Okay, so what happens as n goes off to infinity? What sort of behavior do we expect? Okay, so this is the energy which I wrote down before. The only difference is that I'm going to substitute in the definition of wij. So if you remember wij, right, this is equal to some function which depends on epsilon and depends on the distance between the feature vectors. Right, so I just substituted in this, but I've done nothing else. Right, okay, so what happens as n goes off to infinity? Well, the first thing is we can say as well, if n is very large, then this summation, and you end up by n, this starts to look like an integral. Right, so it starts to look like an integral with respect to the distribution which we're sampling our data from. So let's say we're sampling from a distribution which has density rho. Okay, so all I've done is I can replace the summation with an integral with respect to rho, and then everything else stays the same. Okay, in my next step, okay, so all I've done here actually is a change of variables. So I've let x be equal to y plus epsilon times z. Okay, so this means I can replace the argument here with z. Okay, and this x gets replaced with y plus epsilon and z. And then, of course, if I change of variables, I have to multiply by the terms of the Jacobian, okay, and this kills one of the epsilons to the d. Okay, so I end up with something like, looks like this. Okay, so in my next step, well, if epsilon is very small, then the first thing I can note is, well, that y plus epsilon times z, well, this is going to be approximately equal to just rho of y, if I'm assuming continuity in my density. So I get a rho squared coming out here. The other thing I can look at is, well, okay, u of y plus epsilon times z minus u of y, then if I divide through by the epsilon here, this starts to look like a derivative. Okay, and this is a derivative in the direction of z, so this term here starts to look like this. Okay, so this is kind of all I've done here. And then, okay, this is kind of a little trick you can play using the isotropy of eta, and what you end up doing is kind of being able to pull out one of these integrals as a constant. Okay, so what you get looks like essentially like a weighted L2 norm on the derivative. Okay, sorry, a weighted LP norm on the derivative. Okay, so let's define this as kind of being my continuum energy. Okay, so I mean, so this is maybe a sentence for the people who know some sort of functional analysis. So let's remember we're trying to minimize. So we're trying to minimize this EMP subject to the energy taking finitely many constraints. So we're minimizing EMP subject to this U being equal to some LIs at a discrete number of points. Okay, so in the continuum, right, we kind of want to say, okay, do we have the same problem? So can we sort of look at for U's that minimize this energy subject to U of xi being equal to Li for I equals 1, 2, up to capital N. Okay, so for this, we kind of need some sort of regularity. So in particular, we need to be able to impose pointwise constraints on U. And it turns out that if you want continuity, you need to be able to choose P being sufficiently big. So you need P being bigger than the dimension of the space. And that way, you know that if this energy here is finite, then you know that U is going to be continuous, and you know you can impose pointwise constraints. So this then kind of puts like a necessary condition on the choice of P. And it's kind of natural to say, okay, is this sufficient? And the answer actually is no, it's not. So the problem you kind of have is you can put spikes at your labels, and if these have low energy, then okay, this is kind of very, very bad. Okay, so let's kind of look at let me be more precise. So let me consider a spike at the first data point. Right, so this is just a function, okay, which takes the value 1 at x1. It's going to take the value 0 everywhere else. So of course I could change this 1 for anything else, right? And that would mean that I could satisfy my labels at x1. And of course I could do this for the first sort of first several feature vectors, and that way I could, I could essentially interpolate between the labels that I know and then be 0 everywhere else. So this is what this function is trying to kind of mimic, but just to be a little bit simpler. Okay, so what is the energy of this function? Okay, so if I put this in, so of course, if I'm looking at the difference between u and xi and u and xj, well, if I and j are both bigger than 2, then u and xi is equal to 0 and u and xj is equal to 0, so of course that's going to be 0. So the only cost I pay is going to be when I is equal to 1 and j is equal to 2. So when j is equal to 2 or more, so what this means is that my energy is going to look like this, essentially. Right, okay, so I can now look at this, and if I think back to my kind of typical example of eta, where this is only going to be positive if the argument is less than 1, then what I can realize is that actually this is just counting the number of data points that are within a ball of epsilon of the first data points. Okay, I think is there a question? Someone's got their hand up if you want to unmute yourself.
Okay, after the session, we can start the question answer.
So what was that? Sorry.
After the session complete, then we can start the QA session.
Okay, that's fine.
Who is there actually? We couldn't identify this one. Okay, no problem. You please continue. Thank you.
Okay, right. Okay, so I can. Okay, so what this term here is essentially doing is just counting the number of data points that are within epsilon of the first data point. Okay, so we kind of know how this is going to scale. It's going to scale roughly as n times the volume of the ball, okay, at x1 radius epsilon. Okay, so that's going to be scale up to a constant as n times epsilon to the d. So if I kind of group if I take out the factors here so that I know that this sort of red term is order 1, then what I get left with is sort of 1 over epsilon n to the p times n. Okay, and what I know now is, well, if epsilon to the p times n is going off to infinity, this means this energy is going off to 0, and this means this spike is free, essentially, in the limits. Okay, and this kind of tells us what we kind of expect to be either in the ill-posed regime or the well-posed regime. So if epsilon n to the p times n is going off to infinity, then this problem is actually becoming degenerate. Okay, and I can make this more precise on this slide here. So, okay, so if un is a sequence of minimizers satisfying the constraints, then, okay, I automatically know that un is going to converge. Okay, and the question is, what's it going to converge to? So if n times epsilon n to the p is going off to 0, then this is the well-posed regime, then u is going to converge to a minimizer of my continuum energy with the constraints. On the other hand, if n times epsilon to the p is going off to infinity, then this u is just a constant. So what this says is that if I don't scale my graph correctly, then my minimizers are just converting to constants. So this second regime is very, very bad. And this is something that we would want to avoid. Okay, so there are kind of several other results in this sort of area, which I just sort of given a few references to here. Okay, so let me kind of show some pictures so you can kind of really see what's happening. Okay, so this is going to be a 2D example. So I'm going to work with p being equal to 4. Okay, so our data now, if we look down on these, right, this is how we would see our feature vectors. So they're kind of all in the plane. So between 0, 1 squared, and I think it's uniformly distributed. I have 2 labels. So one label is around here. So this is label at 0. Then I have a label up here at 1. And then I've computed my minimizer so in the discrete setting. So the labels are kind of given by in the z-axis. Okay, and then I've just plotted the grid to kind of make things easier to visualize. I've done the same thing in the continuum domain. So again, you can see, I've got my constraint here, and my constraint here. Okay, and then I've just solved this problem on a very fine mesh. Okay, so let's now look at what happens if we play around with epsilon, and let's look at what happens if we can zoom in around one of the constraints. So I'm going to zoom in around this top constraint here, okay, and vary epsilon. Okay, so the first picture here, this is roughly the same epsilon as I had on the previous slide. You can see we do get like a very small spike around the constraints. Yeah, okay, and now if I increase my epsilon, so if I double my epsilon, you can see the spike gets bigger. If I double my epsilon again, right, the spike gets even bigger still. So what you can kind of see is that as epsilon is getting bigger and bigger, this spike is getting bigger and bigger. And what this means is that actually my solution will be getting flatter and flatter. So when epsilon is too big, essentially my solution is completely flat, but just with a spike, here, and then the spike down here. Okay, so let's try and sort of explore what's going wrong, and let's restrict ourselves to p being equal to 2, and this way we can use the random walk interpretation. Okay, so I need to explain what the random walk interpretation is. Okay, so we have our graph, we have our edge weights. We're going to let t of x. This is going to be the random walk on our feature vectors. Okay, and we will initialize this. So x of 0 is just going to be equal to x. Okay, so this is some point which we can pick on our graph, and then we'll transition. So if we're currently at the point xi, then we will jump to the feature vector xk with probability that's proportional to the weight of the edge. Okay, so this now defines a random walk. So we pick somewhere to start, and then we transition with probability proportional to the edge weights. Okay, we'll stop our random walk as soon as it hits one of the labeled nodes. Okay, so this S of x is just the first time which the random walk hits a labeled node. Right, so we have a random walk, it moves around, and then eventually we'll hit a labeled point, and then we stop. Okay, so now if I assume my labels are given by some function, let's call it G dagger, this is just kind of for notational convenience, then it turns out that the solution to the previous problem, when p is equal to 2, is given by the expected value of the label when this random walk terminates. Okay, so this is kind of like a nice sort of characterization, and we can use this to sort of understand what's sort of happening and why our problem can be ill-posed. Okay, so let's think about this random walk. Okay, so let's first of all think about how far this random walk can move in k steps. Okay, so xk of t minus x, this is the distance which the random walk has moved in k steps. Okay, oh sorry, this t here of course should be an x. Sorry about that. Okay, so this is the how far we moved in k steps. And what you can probably convince yourselves is that this should scale something like square root of k, the number of steps we take times the size of the steps we take. So this is somehow like a central limit theorem. You can sort of imagine if you take either a step to the left or a step to the right, you're eventually going to end up within sort of one standard deviation. Okay, and that sort of one standard deviation should scale sort of roughly square root of k. And then of course you have to scale by the length of the steps you're taking. Okay, if the proportion of labels is given by beta, then the probability of hitting a label point is going to be roughly sort of 1 over beta at each time point, which means that if the proportion of labels are beta, then the probability of hitting a label data point at any one time is going to be roughly like beta. Okay, which means you're going to expect to take something like 1 over beta steps until you hit a label. Okay, so if you just look then, okay, what's the difference between UN and G dagger? Okay, so UN is the solution which we've which we can write as being the expected value of the random walk at its stopping time. We can write UN as being the expected value of G dagger at X of S of X. Okay, so a simple sort of inequality means that we can just compare G daggers at X and at where the random walk terminates. So if I assume my G dagger is Lipschitz continuous, then this now I can just sort of, this is kind of the same as comparing the expected value of how far this random walk moves when it terminates. Okay, so if I know now that my S of X, if I'm expecting this to be around 1 over beta, so I'm taking sort of roughly 1 over beta steps. Okay, and I know if I take 1 over beta steps, then I'm going to move a distance of something like epsilon over square root of beta. Okay, so what this means now is that I can kind of bound this this gap. Okay, and okay, so of course, like in the previous section, right, where beta is the proportion labeled points, this is going to scale roughly as 1 over n. So actually, this means that this this inequality here is actually blowing up. Okay, one can be a bit more careful with this and get roughly the same bounds I had before. So let me introduce this the second theorem first. So this just says that the it's actually, sorry, this U here should again be a G dagger, I think. Okay, but one has that the maximum distance between UN and G dagger is going to be, okay, epsilon over square root of beta, okay, plus these sort of logarithmic terms, and these logarithmic terms come out if you're a bit more careful than I was on the previous slide. Okay, and one can kind of characterize the probability which always happens to it. Okay, so what this actually gives you is a lower bound on the number of data points which you need. So you know you need at least, so this epsilon over square root of beta, this must go off to 0. Okay, so you know that you will need at least epsilon squared data points. Okay, and we can kind of show that the opposite is true as well. So this first theorem says that if the fraction of labeled data points is too small, in this case it just has much less than epsilon for the p. Okay, then sorry, this Fn also should be a UN. Then UN, the sequence of minimizes, UN is just going to converge to a constant, which is kind of the unposed problem. Okay, I think I'll probably talk about Poisson learning, and then I'll probably skip the last two problems that I was going to talk about, so I can finish in roughly 1 hour. Okay, so this is kind of this is the problem which we saw before, right? So this is an example of some spikes developing. So what we've done is we have two labels here, one here, one here. And what's happened is that our labeling function is essentially all constant, and we've just put a spike at the two labels. So of course, this is kind of nonsense. We want to kind of avoid this sort of problem. Okay, so if we go back to our random walk, sort of interpretation, how we can kind of understand this is that if we don't have very many labels, then our random walk has to move around a lot before it finds labeled data points. And in particular, it can pass the mixing time of the random walk. So what this means is that the random walk has essentially forgotten where it started. So if it's forgotten where it started, this kind of means that our where we finish is kind of independent of our starting point. Okay, so the mixing time of the station distribution of the random walk is itself just proportional to the degrees of each node. I mean, it's not so important. And what's more important is that essentially there is a probability distribution where no matter where you start, you're kind of converging to this data points, to this probability distribution. Okay, so what this is saying is that, okay, if I start off at X, like the probability of me being at Xi, this actually probably should be a limit, is going to be approximately equal to this pi of Xi, which is independent of where I started. So I started at X. Okay, so this means actually I can kind of approximately compute what my minimizer is going to be. Right, so my minimizer is going to be approximately equal to a constant, and this constant is just going to be the weighted average of all the labels. Okay, so now if I actually want to do labeling, then what I would do is I would actually threshold this solution here. And what you can see is that I'm either going to threshold most things as being, so let's say this label here is -1, let's say this label here is +1. So I'm going to threshold things either as being mostly +1 or mostly as being -1. So this plane here is going to be at C, so C is positive, then everything is going to get labeled +1. If C is negative, everything is going to get labeled as -1. Okay, so if I want to kind of, so this introduces a bias, right? Because if C was 0, then maybe I would have some sort of hope. But chances are C is either going to be positive or negative. One thing you can do is say, well, let's just subtract C, and let's, effectively let's do the thresholding at C. This is kind of a strange thing to do, right? Because actually this is kind of the same as, instead of using the labels, this is the same as using the labels after we shift by a constant C. Right, really what I'm doing is I'm just shifting everything. If I'm thresholding at C, what I'm really doing is I'm just shifting everything here downward by C. So then why would we expect to do better if we're using the wrong labels? So this kind of mathematically isn't the right approach to do, even though sort of thresholding at C is perhaps sort of natural. Okay, so let's just kind of look at a different approach. So let's assume that we don't have very many labels, and let's assume that none of them are connected. Okay, so this means that Wij is equal to 0 for all for all feature vectors that are labeled. Of course, we're only labeling our first capital M. Okay, then we can kind of look, what does the okay, so actually I may okay, so I edited this talk for this seminar. I think I may have cut out something which I should probably have spoken about earlier. So this L here is the graph Laplacian. Okay, and what one can show is that let me go back. Yeah, okay, that our minimizers En2, they're going to satisfy an equation which looks like the Laplacian of UN is equal to 0 at all label points, and then UN has to be labels at all label points. Sorry, I think that got cut. But I can kind of look, okay, so we can look at approximately what sort of equation is our minimizer going to satisfy at the label points. So, okay, so if we look at the graph Laplacian of UN, okay, at label points, right? This is actually just the definition of the graph Laplacian. Okay, so this is going to approximately equal to just the, okay, I can reduce the sum from 1 to n to n plus 1 to n, and this is because I'm assuming that none of my labels are connected. And then here, well, okay, so UN star of xi, so xi is a label point, so this has to take the value li, and then my UN star xj, this is a labeled data point, which I know is going to be approximately equal to c. Okay, so I know then that my graph Laplacian of UN star at xi is going to be approximately equal to this. Okay, and I can simplify this as so of course this li minus c doesn't depend on j, and this sum of Wij's, this is just the degree of the node at I. Okay, so what I have is that the graph Laplacian at UN star is going to be approximately equal to the degree times label minus the constant c. Okay, and I kind of have like a mean value condition as well. So again, I can look at what does what does UN star, okay, weighted by the degrees, what is this approximately going to satisfy? So again, I can split the summation up into the label points and the label points. So the label points, I just have the degree times the label. At the label point, I have the degree times the constant c. And then this can be yeah, so in if I use now what my definition of C is, it actually kind of turns out that both of these terms are kind of, both these terms added together are just C times the sum of all the degrees. Okay, so what do I have? I have that the graph of Partitioning UN star is approximately equal to something which is going to be 0 if I'm evaluating at a labeled data point, and it's going to be equal to something essentially equal to di times li minus c at a labeled data point, and I have this sort of mean value condition here. Okay, so this is actually a Poisson equation. Right, so let's go back to what we're trying to do, and what we want to do is rescale our function UN star to avoid these spikes. Okay, so let's define Vn star to be just UN star rescaled. Okay, so I'll subtract B, and then I will multiply by some A. So it's kind of clear that I should probably choose B being equal to C. That way I've got my, the thresholding is going to be around 0. And then it doesn't really matter what we choose A to be, because actually we're just going to use the sign of the function. So this to A can be anything to the which ignore it. Okay, but what I just said, okay, this means we have to find UN star, and then we go and find Vn star. But what we have here is, well-posed equations. And so the question is, well, can we just go directly from these equations and avoid going via UN star? And then it's going to be yes, we can. So if instead we define Vn star to solve this Poisson equation, okay, so what actually I've done here is I've substituted in Vn star equal to UN star minus C. So this term here on the right hand side won't change if you check the algebra, and on this side, this term here, you get you get an extra constant of C on the left hand side, which cancels with the right hand side. So you end up having a 0 mean value condition. Okay, so now the question is, does this, if we start from these equations here, do we do any better? The answer will be yes, but let's try to understand why we expect this to do better. Right, so this is the Laplace learning random walk. Right, so if we remember, if you want to know what label we're going to give it X, right, then we have our random walk, it moves around the graph, and then the two labeled points here are the red ones. So we just look at where we end up, and then we take this label. And of course, we do this many, many times, and we take the average. Okay, so we know that the label for X is going to be the average of labels where the random walk terminates. So in this case here, we're going to the label which is slightly further away. We're probably going to more likely not end up at this label more often. Okay, so then the Poisson equation. So this now, if I want to compute my solution to Vn star, say, okay, does this have a random walk interpretation too? The answer is yes, but it's slightly more complicated. So somehow now this is the dual random walk. So instead of releasing a random walker from the point which we want to label, we now release the random walkers from the labels. So we have two label points. So we'll have two random walks that move around this graph. So we have the blue random walk, which starts at x1, and then we have the black random walk, which starts at x2. And if you wanted to look at the label, so let's say we want to label this point here, we would look at the frequency at which the random walkers visit this label. Okay, and then we somehow average that. So I won't go into all the details here, but this is kind of the equation. But the important thing here actually is that the way one uses the random walk interpretation here is one essentially subtracts the long time behavior. So I cut some of the details, but one can kind of understand this. Okay, if one didn't have the minus C here, then what we would look at is just the fraction of labels which come from the two labeled data points. But this minus C here is essentially describing the long time behavior of the random walk. So what we kind of have is that this our solution is somehow the behavior of the random walk over all times, then subtracted the long time behavior. So somehow now this is only representing the short time behavior of the random walk, and this of course means we get we're more likely to get a well-posed problem. Okay, whereas in this case here, we're not subtracting the long time behavior. So if our random walkers are going to struggle to find the labels, this means that we're only going to detect the long time behavior of the random walk, which is bad. Okay, so I'm just going to show some sort of numerical results, and then I think I'll probably finish the talk there. So we tested this onto 3 data sets. So the first one is the MNIST data set, okay, which is very well known. So this is sort of 70,000 images, 28 by 28 pixels, and they're from digits 0 to 9. You can see some examples here. We also looked at fashion MNIST, which is essentially a drop-in replacement of MNIST. So again, it's the same number of data points. It's the same number of pixels. The only difference is that numbers now have been replaced by items of clothing. So you can kind of see, we have it's like handbags. So one number has been replaced by handbags, and the number has been replaced by shoes. Another number, replaced by jumpers and that sort of thing. Okay, so both MNIST and fashion MNIST are kind of considered fairly toy data sets. So we also look at CFAR10. Okay, I assume we didn't write down the number of images, but it's I think much bigger, and this is considered a much more complicated data set. And we have all sorts of classes, so we have pictures of planes, cars, birds, cats, and so on. Okay, so we'll look at sort of how well our method does. So we compared with a whole host of other methods. Anything that can do semi-supervised learning, we can compared with. So the Laplace learning, this is the Laplace recognition method, and these are the methods I won't really go into. Let's look at what sort of accuracy we get if we only have one label per class. Okay, so for example, for MNIST, right, we have 10 classes. So here we only have, if we have one label per class, we only have 10 labels across our whole data set. And what we can kind of see is that our original method, Laplace learning, or Laplace regularization, this only gets an accuracy around about 16%. So of course, if we were just to assign labels by chance, we would expect to get at least a 10% accuracy. So 16% isn't much better than chance, really. Whereas this process learning method, okay, gets more than 90%. Now, as we increase the number of labels, so we have 2 labels per class, so 20 labels in total, you can kind of see that our method, of course, improves, but the Partitioning learning method, this also improves very much quicker. Okay, if we have 5 labels per class, we're still much better, but the gap is narrowing. Eventually, this Partitioning learning will probably overtake Partitioning learning, but you can see you need enough labels for that to work. In the low label rate regime, really Partitioning learning is state of the art. It is kind of a similar story for fashion MNIST and the WebKB data sets. Very few labels. The Partitioning learning does kind of much better. So here, of course, it's a harder problem, so the accuracies are much lower, but still one label per class, we get close to 61%. I guess I'm going up to sort of 72% for around 5 labels. And kind of similar story from WebKB. Okay, so I think to allow some time for questions, and I've already spoken for an hour, so I think probably people's attention spans are starting to wane. So I'll just sort of skip to the end, but I had also prepared slides and sort of Ginsberg presentation. So this is kind of the problem of, if you're given an image and you want to separate it into, say, like foreground and background, how can we do this? And this is kind of one method, and you can kind of see this toy example that it's green is background, red is the foreground. I was going to describe some theory around this. I was also going to talk briefly about Cheeger cuts. So this is kind of the problem of separating a data set into 2 components. So here, if you want to separate into 2 components, okay, a natural sort of setting is to just cut edges and then count the number of edges you cut. Okay, so this defines like a cut functional. Here, okay, but the problem is now this is actually kind of trivial. What you would do is you would just say, so AN is going to be, so we're going to divide our graph into AN and AN complement, But to minimize this is very easy. You just define AN to be the empty set. If AN is the empty set, then of course you're not having to cut any edges. So everything's very easy, but this is kind of unsatisfying. So to kind of get around this, people sort of introduced either sort of additive terms or sort of balanced terms. So the Chiga cut uses a balanced term that looks something like this. So this on the top, this is just the cut. So this is you're just counting the number of edges you cut between A and A complements, and then at the bottom you divide through by the size of A or the size of A complement, whichever is smaller. So this means, of course, if you set A to be the empty set, right, then you have to divide through by 0. So of course, this is not going to be a minimizer. Okay, and yeah, I'm going to talk just a little bit about some theory. Essentially, what happens setting this off to infinity, and do you get convergence? And the answer is going to be yes. You would converge to a continuum problem, and actually we can give rates of convergence. And by comparing to isoparametric inequalities, we actually also give rates of convergence for the Chiga sets. So the Chiga sets are the minimizers. So essentially, yeah, this is going to be so. Here, this AN star is the best choice of Chiga cuts, and what you can kind of show is that this is going to converge to something which solves a continuum problem. Okay, so I think I will pretty much finish here. Let me maybe just sort of advertise a seminar series which I'm involved in organising. This is the One World Seminar Series in Mathematics and Machine Learning. It's every Wednesday. Unfortunately, the timing isn't particularly friendly in India. I think it starts at 9:30 in the evening. But we put the videos onto YouTube, so you can always sort of catch up the following day. Yeah, so with that, thank you very much. And yeah, I'm happy to take questions.
Thank you, Dr. Matthew. Our program chair, Dr. Marka, please take over the session.
Sir,
Thank you very much, Dr. Matthew, and it was really insightful. And most of our participants, especially those students who are from mathematics background, so and most of them are just entering into this field of data science. They're just starting their data science program with us now. I hope they enjoyed and they have got good insights into the way the different mathematical concepts such as from linear algebra and other calculus and other areas are being used very effectively in the field of machine learning, and we appreciate and thank you for enlightening on this. Now I request any participants, if you have any questions to the speaker, you may please ask.
sir, good evening, sir. Matthew, sir, good evening. And sir, can you, sir, go to the page 28, sorry, slide 28, sir.
Yes.
So what is the meaning of LIP and how to slide 28, sir, slide number 28, sir.
This slide here.
Yes, sir. So what is the meaning of LIP, sir? And sir, G, sir, this is a function of x-axis. This is the isometric function. So, sir, how to this step to this step, sir? Actually, G is a function of x-axis, sir, and you take here E is equal.
Okay, yeah, sorry, I didn't explain the notation. So, yeah, LIP is just the Lipschitz constant. So essentially, this is yeah. I mean, if G dagger is is differentiable, this would just be a bound on the derivative of G dagger. So it's just, yeah, essentially, it's just, I guess it's a very strong notion of continuity for G dagger. Was that your question? Sorry, did you ask something else as well?
Sir, my question, what is the meaning of LIP? LIP?
Ellipsis, sir, he answered. Ellipsis.
Yes, the Lipschitz bound, or you can think of it as being
Okay.
an element bound on the derivative of G dagger.
Okay. Okay.
Yeah, I've seen in the chat someone's asking if I can share slides. Yeah, I'm quite happy to do that. I don't know if, so Dr. Santanu, if I send you the slides, can you sort of distribute them, or how do you want to?
Sure, sir. Actually, YouTube live streaming also going on. Okay, so they can watch from there itself the whole session.
Okay. Yeah, but I'm quite happy to share slides as well. If people want
Yes,
to.
share, then we can share with everyone, no problem. So, any further questions from the participants, please?
Maybe I can make one sort of closing remark. I guess what I kind of tried to get across in this talk is that I guess that maths can be really useful in these sort of situations. I think there are, I mean, sort of fairly, on the face of it, these sort of mathematical techniques seem fairly sort of abstract, things like sort of gamma convergence and compactness results. And perhaps when you're sort of studying these in sort of, you know, as an undergraduate or as a postgraduate, you kind of think, what's the point? But actually, they kind of really have, they really are very useful tools when you're sort of analyzing these sorts of machine learning type problems, and they really kind of, you know, are the right framework. So, I mean, I really have a calculus of variations background, and arguably I would describe myself more as a calculus of variations person than I would as a data scientist. But I certainly work on data science problems. But, you know, it's, my background really was in sort of calculus of variations and applied analysis. So I'd sort of encourage people, if you are interested in data science, maybe stay in applied maths for as long as you can, and then make the switch once you have the sort of tools in your toolkits.
Yes, perfect. That is all calculus, the graph theory, and then other stuff of mathematics actually you are using here, right? For more machine learning aspects. And that is actually the mathematicians work like that, right? So you can approach to the computer science background, or maybe you can deep into the data science as a statistician also, right? So one kind of blended kind of work you observe here. And one just very curiosity, that is the last slides that you showed regarding your validation, right? Your result with the image processing or maybe pattern recognition kind of stuff. So could you just briefly, can you just repeat actually how you could validate your results using this machine, this image processing aspect? Yes, previous.
So is this, am I on the right slide?
Maybe 36.
Okay, right. Yeah. So, okay, yeah. So I guess, okay, so what I like about this sort of Poisson learning example is that actually it kind of really only comes, so the whole method was, one has to kind of understand the maths to get to it. I think it's not obvious that you wouldn't just pull this equation out of thin air. You kind of really have to go through the maths and understand, first of all, why the original method failed. And then second, you have to understand how to kind of correct this with a sort of ill-posed equation. So with a well-posed equation. So, you know, we took, so this Laplacian learning or Laplacian regularization is kind of very popular. If you look at the original paper, it has kind of thousands of citations, you know, it's, you know, everyone really loves it. But the problem is it doesn't really work very well at low labeling rates. So this is kind of what we show here. So this is just the accuracy. So we know, because this is a toy data set, we know what all the labels are. So, you know, we take, okay, so here we take one label per class, or, you know, 10 labels in total. And then the other, we have 70,000 images. So, so 69,990 images are unlabeled, but we know what the labels are. So we kind of estimate the labels, and then we compare, we compute our error rates. And what you get, of course, right, is in this sort of, the original but very popular methods, right, you get a really bad accuracy. Okay, and this is because, and this is what we've kind of shown, is that essentially you're looking at an ill-posed problem. So you're looking at an ill-posed problem, so essentially it's garbage. But then if you kind of, sort of go through the mathematical analysis, you can realize you can actually correct this equation. And then, so Partitioning learning really is just a bias-corrected version of Partitioning learning, but you can see that the accuracy drops from 16.1%, and it rises all the way up to 90.3%, which is a huge difference. And this, again, is only possible using sort of, understanding the mathematics behind the method.
Yes.
Yes, this is
Fine. Thank you. Thank you very much for this explanation. So many students are there who are entering to the data science programs, as well as the many research scholars and then other faculty members also attending this program. So one from mathematics part, I have one question, maybe not question, is a curiosity, that is graph theory, how you are attaching with this machine learning stuff. So you have used some graph theory aspects, right, in your work?
Yeah, I have. So, okay, so actually what I really like about my work is that it uses so many different things from so many different areas. So the graph theory actually kind of gets hidden sort of behind it. So it gets hidden away. So I think on one of my very first slides, I had, I sort of said, one needs to choose epsilon to be bigger than the connectivity radius of the graph. Okay, so that the graph stays connected. Actually, this is basically the only sort of graph theory that we really use in the whole theory. But of course, the graph theory gives us the rate. So graph theory would tell us that we have to choose our connectivity radius, which is epsilon. It has to be at least log n over n to the d power. Okay, where d is the dimension of the space. And actually, even that we don't explicitly use those results in our own results. Actually, we make a connection to optimal transport. And in optimal transport, we look at the distance between the empirical measure and the continuum measure, and we can measure this in an optimal transport framework. So, so we've gone from like graph theory now to optimal transport. And then, of course, you've seen that the probability theory we use, so we kind of have to analyze all these random walks. Then there's the calculus of variations sort of aspect. So we have the gamma convergence, and we have all these sort of compactness results and modularity results. So we really kind of span a lot of different areas of math, which I think is quite exciting.
Yes, very good explanation. Thank you so much. Actually, you are showing us one by one that the blending kind of thing, that one mathematicians can proceed to different aspects on application-based problem, right? Instead of this on our CSE guys also doing the same thing. So all CSE stops are there, computer science. So thank you so much for the explanation. So Dr. Marka, if any questions from the participants.
Yeah. So would you like to give any suggestions to, in continuation to what you have already gave, to early stage data scientists, how mathematics, what type of mathematical concepts or tools will be very much essential for their data science career? Could you please throw some light on this?
Okay, that's a very good question. I guess it depends a little bit on what kind of areas of data science you want to go in. So, and one of the reasons why I really like these graph-based methods is because I think there is really like a very deep mathematical theory, which is kind of, one can kind of really get their teeth into. So, I can kind of repeat that, things like calculus of variations is very important. Probability theory, optimal transport, PDEs. So I didn't mention this before, but the one can kind of use sort of PDE arguments to analyze these things as well. And every area kind of has its own advantages, disadvantages. And of course, a lot of the time, there's multiple areas coming together. So for this sort of graph-based work, they're probably the most important. For neural networks, that's a bit more outside of my area, but I think there's sort of, I mean, I'm part of a program at the moment, which is kind of looking to sort of, I guess, make progress in sort of the theoretical understanding of neural networks. But there, I think something like dynamical systems is kind of very important. There's a lot of people making connections between sort of particularly deep sort of ResNets and dynamical systems. I would always take Highest variations because I'm biased in that way. Yeah, sort of, approximation theory, this sort of thing. So, I mean, actually, if people want to know more about the sort of, theory of deep learning, if you go into the Isaac Newton Institute webpage, I think you can watch the videos from the work. There's a workshop going on this week, actually, and there's sort of many talks there which you can sort of welcome to watch. And again, actually, my One World seminar series, we've had some very good speakers. So people like Weenan E from Princeton, he gave the opening talk, and again, he makes a lot of these connections, and I think he can give some sort of pointers to the kind of the right sort of settings to work in. Perhaps, the one area which kind of unites everything is probably a good background in functional analysis. So functional analysis is kind of tough, but I think it's kind of rewarding, and it's kind of the right setting mathematically for many of these problems.
Thank you, sir. That was indeed insightful.
Yeah, maybe I can also say that, I guess this is my opinion. I mean, there's, I think particularly with things like neural networks, I wouldn't say there's a right answer. I mean, I think we're still trying to understand these problems. So I won't want to, I mean, it might be in 5 years' time, my answer that I gave today is completely nonsense, and that there's really, there is a right way to analyze these, and it's not what I just said. So I guess that's the sort of the caveats that, yeah, I don't want to be held. I don't want my words to come back and bite me.
Yeah, true. The advancements are moving at such a rapid speed that's possible.
Yeah, exactly.
Thank you, sir. Yeah. Thank you, sir. Thank you, Dr. Matthews, for such a nice talk and for your insights as well. Now, if the participants have any questions, you may now ask. If not about the task that was given, if you have any questions regarding your the data science program or the program at BSc, MSc programs at our university also, if you have any questions, you may please ask.
I think no questions, sir.
Yeah, so we assume there are no further questions, and thank you very much, Dr. Matthew, for your wonderful talk, as well as all the participants for your participation and taking time and attending the session. Thank you all. Thank you very much.
Thank you, sir.
Yeah, thank you, and thank you for the invite.
Dr. Matthew.
Thank you, sir.